We've been looking at functions, and we know that there are many different types of functions, okay? We've been looking at quadratic functions. What is a quadratic function? How do we define it? It's a parabola. But how do I know that something like this is a quadratic? The power of 2. If I have something like this, what kind of expression is this? It's a linear function. Why? Because it's got a power of 1. And also graphically it looks like a line, right? Cubic functions, no guesses there, right? A function where the highest power is 3. So for example, y equals to x cubed is your basic cubic function, right? Just graphically, what does this look like? It looks like this. And just some like kind of basic features about this curve, right? It looks like this. What do you notice about this particular function, Harry? Yeah, it looks kind of funny, right? It looks kind of like it wraps around a little bit. What type of function is this? We can classify functions, right? This is a odd function. And we can prove that algebraically. Remember your definition. F of negative x equals to negative f of x, right? If you put that into this type of expression, you'll see that this is actually an odd function. What's the other way that graphically we realize that was an odd function? We could rotate it 180 degrees, okay? That's right, yeah. Rotate 180 degrees, rotational symmetry. That is my cubic function. But that's the basic cubic function. It won't always look like that. We can do certain kind of manipulations to it. Let's look at this first one. Y equals to kx cubed plus d. Now this is the kind of like one of the general forms that we have. And Desmos is really great because one thing with functions is that in order to see the relationships, I don't want to just tell you them. I want to see if you can work them out for yourself. And hopefully that way you'll be able to remember them much better than me just telling you what happens. Did anyone recognize what happens when that value of d changes? What actually happens? Yeah, okay, so let's see what's happening. Right now it's at 0. You can sort of see the equation there. If you're shifting it up and down, you can see it goes, well, literally up and down, right? So it's kind of like if you remember your linear functions, right, the number by itself at the end was the y-intercept. And if I have it in this form, that's going to be the case as well. So you can either think of d as the y-intercept, or I like to think of it as d changes, d, right, we'll shift it up or down, depending on the value. Interestingly, right, if you shift it up, for example, let's make it 5, is this still an odd function? No, why not? Yeah, good. Remember, it has to have rotational symmetry about the origin. Okay, so even though the shape has remained the same, okay, even though the shape has remained the same, it's not an odd function anymore because it's not rotational. Doesn't have rotational symmetry about the origin. What about this k now? Did anyone realize what happens when k changes?
Like when it gets bigger, it gets steeper.
Okay, so the way we classify is, let's see what happens when we get really large values. It gets steeper, cool. And if we get smaller values than 1, right, you'll notice, oh, it starts to kind of, I don't know how you would like to say, maybe it like gets a bit wider or fatter, right? If you zoom in a bit. All right, there we go. Until what happens when I get so small that I go into the negative values, what happens? Ooh, it's doing a little dance, right? There's your cubic little function dance. It actually goes and it wraps around, okay? It changes the kind of orientation. Yeah, it's like a little spaghetti dance, right? Okay, so k, right, as we get larger values, I guess you want to say narrower. If we get smaller values, it gets wider. And I guess I heard someone say it kind of changes the curvature. You might want to think about it like that, like the curvature of the shape is changing. But the important thing to know is that if you get negative values, right, what happens? The kind of orientation swaps, right? Okay, so now I'm looking at this kind of form here. Let's put that back to 0. What's different about this one? Well, this time, something like this. Okay, k is still, like all the values I'm showing you, they always kind of affect the same thing. So k will always affect the curvature, right? A though is different. A is now, what's different about A? It's, compared to this shift, it's inside the bracket. And that's going to be something that's going to change it differently. And think back to your quadratics. When you change something inside the bracket, what happened? It moves it along the x-axis. Good. It moves it, I guess you want to think about it as left and right maybe. And that's exactly what happens here. As you change this A value, I'll zoom out because I've zoomed in too far. As you change the A value, it moves it left and right. Yeah. And I guess you want to think about, okay, what's actually happening here, right? What's actually happening? Well, I know A shifts it left and right, so I'll write that down first. Shifts left and right. But if you want to think about why that's actually happening, if you take, for example, y equals to x minus 1 cubed, or y equals to, I don't know, x plus 5 cubed, right, you can think about it like this. What's the value of x here that makes this equal to 0? It is, in this case, it would be 1. In this case, it'd be -5, right? So you want to think about the shift as saying, okay, if A is equal to 1, where does it move to? It's moved to, yeah, it's moved to x equals to 1 because that's the point where your whole graph is equal to 0. So you're kind of shifting this point here, okay, this point here. And the same thing if we made A equals to -5, right, then we shift all the way to, what value did I determine? Well, when x equals to -5 there. Can you guys see that, right? So we're looking at the different relationships that are occurring here. This point here, by the way, this has a name. So kind of like how parabolas had a vertex where it went from either maximum or minimum, right, where the gradient changed. Here, something else is changing. The gradient's not changing because it's staying positive the whole time. Something else is changing. The kind of curvature, or we call it, yeah, well, we call it the concavity. The concavity is changing. If you think about where this kind of space is, so we kind of think about like, you know, the curvature here. Yeah, can you guys kind of make that out, right? If you imagine like this was a part of a parabola, this would be concave down, and this would be concave up, right? Can you kind of see that, right? So two sections of our cubic. This is called an inflection point, or a point of inflection. Okay, so that's something we're going to explore later on, okay, but that's just for reference now. It's called a point of inflection, where the concavity of a cubic function changes, okay? Cool. So that's that one there. So A shifts it left or right. What was our last form? What was our last form? Now this one looks really long and complicated. It's actually not. It's actually really good. Number between 1 and 5, Joel?
4.
Number between 1 and 5, Angus? That's different. 3. And I'll put -1. Here's my cubic. What have I highlighted here for you? What was our equation, by the way? What did I even say? X minus 3, x minus 4, x plus 1. Okay, so this is our equation. What do you guys notice? Okay, these are the intercepts. If you look at these, right, think back to when I was looking at this one, right? I'm looking at when the graph is going to be equal to 0. Right, another word that we call those are the roots, right? So hang on, at x equals to 3, this whole thing is going to be equal to 0, which is what you have here. At x equals to 4, you're going to have this whole thing equal to 0, that y value, which is what I have there. And well, what's the value of x here that makes that equal to 0? It's -1, which is our other intercept. So what can we say about A, B, and C here? Are the x-intercepts, yeah. Or we can also call them the roots of our equation. Yeah. Any questions on that?